Hi, my name is Jarman, and in this video, I'll be showing you how to use the error band command inside gridmo. This video is broken into 4 parts. 1, I'll be providing some background to the topic of error bands and why they exist. 2, I'll be describing the 3 most common error band methodologies, as well as some other methodology considerations. 3, I'll go through the error band command inside of gridmo and how it can be used. And finally, I'll provide answers to some of the most common questions from engineers using the error band command. Let's get started. Often in power systems analysis, you may need to compare the results of channels which would ideally be identical, but which are not identical in practice. It is possible to compare the channels qualitatively, whereby an engineer may look at the results visually and make judgments on whether the channels match closely enough. However, such an assessment can be time-consuming and error-prone. Therefore, error bands are a useful quantitative tool to compare channels. The most common applications are used to compare the results of either comparing dynamic power system simulation results, like PSSE, with real data which may come from hardware-in-the-loop testing or on-site commissioning. This comparison is used to compare how closely a power system model matches real-world behavior. A second common example is comparing dynamic power system simulation results from different software vendors. For example, comparing the results of RMS software, such as PSSE, with EMT software, such as PSCAD. There are 3 very common error band methodologies. The first methodology is a vertical offset, with the command of gridmo shown in the bottom left-hand corner and what this would look like on a graph. As we can see from the image, the channel is moved up and down a certain amount of this vertical offset, and that becomes the error band. The second most common error band methodology is a horizontal offset, again with the gridmo command shown in the bottom left-hand corner. For a horizontal offset, the signal is shifted left and right like spreading butter, and that forms the error band. The third most common error band methodology, again with the gridmo command at the bottom left-hand corner, is a delta offset. In this instance, you can look at 2 values. In this example, it's the start value of the simulation and the end value. Alternatively, it could be the start of a transient window and the end of the simulation. But in this instance, we take 2 values and then we look at the difference of those values, and the delta is a percentage of the difference of those 2 values, and that forms the error band. Other considerations when looking at the methodology. It's common to use different methodologies inside and outside of transient windows. When looking at comparing the results of channels which would ideally be identical but are not identical in practice, often that more allowance is given inside transient windows, because during transients, it's harder for these 2 channels to match. This could be when comparing 2 different softwares, for example, like an RMS software like PSSE and an EMT software like PSCAD. The transient behavior might be quite different due to underlying differences in the way the software works. A second common consideration is to calculate the number of data points in a channel which fall within the error band. As part of this quantitative analysis, it would be useful to engineers to know what percentage of points fall within that error band. In this example shown here, again with the gridmo command shown in the bottom left-hand corner, we have a blue channel. It has a vertical offset of 10, in this instance up and down, and we have a second channel in the red, and we're comparing how closely it matches with the blue. And in this instance, we have parts of the signal which do fall within the error bands and parts which do not. We can also see the legend description that is generated by Gridmo, where it'll give you a ratio of the data points, the number of data points which fall within the error band compared to the total number of data points, and also the percentage. And this calculated number can be used as a quantitative metric to figure out how accurately these 2 channels match. So let's look at the error band command inside of Gridmo. In this example, I'm comparing the results of 2 different QREF steps. For the purposes of this demo, both channels are coming from 2 different generic PSSE models, but the same demo could be extended to comparing any 2 channels. So we have a plot of reactive power at the connection point, and ideally these signals that are being overlaid would be identical, but they are not. And at the moment, the subplot has no error bands that's being produced, but let's use error bands to quantitatively assess how closely they match. And in this instance, let's say that the blue line, channel 1, represents the actual real life response, and red is our model. So we're trying to see how closely the model matches reality. So jumping back into gridmo, we need to apply an error band command. Now let's start with something simple, where we can just add a simple vertical offset of 10 up and down, and let's display the calculation. So let's apply that and launch. After running, we can see a vertical offset error band has been applied, and Gridmo has calculated the number of data points of channel 2 which fall within those error bands. We can see the number is 87.4%. This simple example is useful. However, I would like to have two different sizes of error bands now. I would like to keep the vertical offset of 10 within the transient window, but have a tighter requirement outside of the transient window of only a vertical offset of 2. So let's go to our error band calculation and update the command. So firstly, because we have transients, we want to tell Gridmo that there is an event being applied at 2 seconds. Additionally, the vertical offset of 10, we only want to apply inside the transient windows. Then we want a different type of band, still a vertical offset type, but I want that to be a smaller offset, and I want it to apply outside of the transit windows. You can see in Gridmo that you can have multiple types of bands and provide multiple pieces of logic to form quite complicated commands looking inside and outside of transient windows. Let's apply this and run again. After running, we can now see the existing vertical offset of 10 inside the transit window, but the tighter vertical offset of 2 outside of the transit window. This tighter requirement outside of the transit window has meant that fewer data points of channel 2 are falling within the error band, as you can see between 0 and 2 seconds of this signal. Therefore, the number of points falling within the error bands has gone down and is now only 63.2%. Let's now go through some common questions that engineers have when using gridmo error bands. First question, if multiple channels are present, which channel is chosen as the reference signal for the error band, i.e. which signal is the source of truth? In this instance, this is an engine setting. If you go to your engines and navigate to the advanced tab, you can see down here there's something called plot order. These are the default settings currently, and this order is what's respected when choosing which is the reference signal. In this instance, the default is based on most likely what is the most accurate signal, starting with real data coming from site, and then EMT software, and then RMS software. But please note that this can be changed if you'd like the reference signal to change. Can I combine multiple bands? Yes. As we've seen in the previous example, you can have multiple bands in the error band command argument. The bands can have the same logic, like here in the example, there are 2 vertical offsets, or they can have different logic. And you can also specify where that band applies, inside transient windows, outside transient windows, or for all the data. How can I analyze each transient event separately? In this new example, you can have 2 different error band calculations. You can see one here is going from time equals 1 second to 6 seconds, and another one going from 7 to 12. This is done by having 2 different error band calculations. If I come back to the subplot here, I can see that I now have 2 error band calculations, and I can use start t and end t arguments to divide up the error bands, and that means I can get 2 different error band logics as well as 2 different calculations. And lastly, what happens if the amount of data is different between channels being compared? Sometimes when you're comparing model to site data, you might not have enough site data to fool the full simulation. In that instance, the calculations only occur when you have data from both channels. Thanks for watching.